Okay, so in the last class we were discussing, so recall that our goal is the following. So we're given a particular function f which is differentiable, and we also have a set of constraints. So we want to look for the minimum of f of x within some constraint set omega. And right now the problem that we are trying to address is, suppose I give you a particular x that lies in omega, is this x a solution or not? That is what we want to determine, right? And in order to go about this, I define the notion of a feasible direction. So a feasible direction is any direction at the point such that along that direction you can move a little bit and still lie within the constraint set omega. And we say that a point is within omega is a local minimum if for every feasible direction the function value always increases. It can't decrease any further along every feasible direction. All right. Okay, so given this, let's quickly look at an example, sort of a visual example. Suppose I have some function and my omega is, let's say, a to b. Okay, my omega is an interval, and the function looks something like this. Okay, this is f. This is f of x. Where are all the local minima? How many local minima does this have? Okay, the number of local minima is 3, right? Does everybody agree? So what are the local minima? Of course, the most natural one are these two, right? These are interior local minima, but this also has a local minimum at a boundary point, right? Because there is a direction which is basically in this direction. The function value, okay, so for a function on R, there can be at most two feasible directions, either to the left or to the right, right? And in this case, at this particular point A, there is only one feasible direction, and along that feasible direction, the function value is only increasing, right? So it's a local minimum. Similarly, if you take this particular point, it's an interior point, so there are two feasible directions, and along each feasible direction the function value is only increasing. If I take any other point, let us take this particular point, there is one feasible direction where the function value is decreasing and one feasible direction where the function value is increasing. So it's not a local minimum, right? Any questions in the first bench? Any question? Okay, so it's good. So now that we've established the feasible direction the local minimum can either be an interior point, which is what we generally think about when we say local minima, but it can also be at a boundary point. And at the boundary points, interesting things can happen. Okay, so now how do we determine whether a given point, interior or not, is a local minimum or not? So first we look at a set of necessary conditions for a point to be a local minimum. The first that we'll see are the so-called first order necessary conditions. Okay, so it basically says the following. So some x star in omega is, when I say first order, typically when we say first order or second order, it usually corresponds to some property of the first order derivative if it is first order, or second order derivative if it is second order, right? When it is some property which deals with just the function value itself, we typically say a zeroth order something, right? So the first order necessary condition is essentially a necessary condition which tells us something about the first order derivative or the gradient. So x star is a local minimum of the function f within omega only if the following happens. For every feasible direction, what do you think should happen? It should increase, or what can you say in terms of the directional derivative? So the directional derivative along every feasible direction should be greater than or equal to 0. The most natural thing that you think of. So gradient f of x star dot product with v is greater than or equal to 0. Again, remember what our definition of a local minimum is. For every feasible direction, we want to make sure that as long as this delta is less than some quantity beta v, this function value is always less than or equal to this f of x star plus delta v. Okay. Let's see a quick proof of this statement. How would you go about trying to prove this? Okay, so it's the other way around. I'm sorry. So we should assume that it's a local minimum, because if it is a local minimum, then this should be true. If this is true, it's not guaranteed that it's a local minimum. It's only a necessary condition. So
assume there is one direction in which it's expensive.
Okay.
Therefore, it's not.
But how do you prove that? So what is it that you know that relates the function value with the gradient? Again, f could be an arbitrary function. Any guess? How do you relate f of x with gradient of f of x star around somewhere close to x star? Most natural thing is, let's start with Taylor series approximation. So first order Taylor approximation. So we know that we can write f of x to be equal to f of x star plus gradient f of x star times x minus x star plus something that decays much faster than norm of x minus x star. Right, this holds true for every x. But now we are already given a particular direction, a feasible direction v. So we just want to check along every feasible direction v. So let's do that. So f of x plus delta times v is equal to, sorry, f of x star plus delta times v is f of x star plus gradient f of x star times, what is x minus x star? It is just delta times v transpose plus little o of delta, because v is a unit vector, so the norm of delta times v is just delta. Okay, now what is it that we want to show? We're given that f of x is a local minimum. Okay. So let's go about trying to prove the contrapositive. If the gradient is negative along the feasible direction v, then it cannot be a local minimum. That's all what we want to show. So suppose that the gradient f of x star, essentially the directional derivative, is something that is strictly less than 0. Okay, let's say that this is equal to some minus epsilon, for some epsilon greater than 0. Then what can you say? What is f of x star plus delta times v? This is equal to f of x star. So this is just delta times the inner product between f of a gradient f and v, which we know is minus epsilon. So this is just minus epsilon times delta. Epsilon is fixed, it is some fixed number, plus little o of delta, right? Something that decays much faster than delta. So if you take a small enough delta, right? If delta is sufficiently small, then for all delta less than some particular quantity, this term dominates over this particular term. Right? This is f of x star minus whatever delta or epsilon delta times 1 plus or 1 minus little o of delta divided by delta times epsilon. So as delta vanishes, this quantity tends to 0, right? Which means that this whole quantity is strictly negative. This is less than 0 for all delta which is sufficiently small, let's say below some particular delta star. So which means that in the neighborhood of x star, f of x star plus delta v is strictly less than f of x star. Is less than f of x star for all delta less than or equal to some particular delta star. Which means that it's impossible for this to be a local minimum. Basically, what we've shown is that if the directional derivative is negative along even one direction, then this point cannot be a local minimum. So if x star has to be a local minimum, then along every direction, the directional derivative should be non-negative, should be greater than or equal to 0. Right? So now suppose that x star is an interior point.
You know, explain what is happening.
Where?
1 minus O delta by delta.
This part. So what does this mean? It means that for all sufficient, so when I say little o of delta, right, it means that the limit as delta tends to 0 of this quantity is 0. All right, or in other words, no. The notation that, so we're only interested in delta that is sufficiently small, right? So when I say little o of delta, again, it's notation, nothing else. This basically means that limit as delta tends to 0, little o of delta divided by delta, this is equal to 0.
Sine of delta belongs to delta.
I'm sorry?
Sine of delta is over delta.
The sign could be different, doesn't matter.
Sine.
I didn't quite understand. What do you mean by sine function? Which? Okay.
That is over delta.
Okay, sure.
But the limit as delta tends to 0.
The limit as delta tends to 0 is of what?
Sine delta by delta.
Okay, so
That statement doesn't.
why do you say that sine delta is little o of delta?
The definition for all C where X is an N such that sine of.
So you have to be a little careful, okay? So when you talk about asymptotics, so typically I agree. In many cases, particularly when you're talking about sequences, right? You look at asymptotics as n or some particular quantity tends to infinity. Right now, we're essentially interested in asymptotics as delta tends to 0. Okay, or if you're not comfortable with the notation, let me just say that this is equal to this plus some, say, g of delta, with the property that limit as delta tends to 0, g of delta by delta is equal to 0. Okay, because in the end, this is going to be some series which has all higher order terms. It is something times delta square plus something times delta cube plus something times delta to the power 4 and so on. And when you divide by delta, you get some other series which is of the form delta plus something times delta square plus something times delta cube and so on. So as delta tends to 0, this tends to 0. Right? Is that okay? So now is the rest of the proof okay? So again, in typically when in computer science, when someone says little o of something, typically it is in the regime where the some parameter which tends to infinity. Right? But here we're using it in a slightly different context. We're using the asymptotics when this parameter is tending to 0. Any other question? Delta star is some quantity. This delta star is some fixed number that could depend on x star and of course on f, right? X star comma f, but for our purposes it is some number. So in this case, right, the first order necessary condition, if x is a boundary point, then not all directions are feasible, right? Only certain directions that take you to inside the constraint set, only those are feasible. But now if you take an interior point, then all directions are feasible. In this case, we can say something which is easier to verify. Then x star is a local minimum only if, can you guess what the rest is? Something about just the gradient. What should be the gradient of f? Should just be equal to 0, right? They're saying that x star should be a stationary point of f. Again, this is only a necessary condition. Just because the gradient of f at x star is 0, it doesn't mean that it should be a local minimum. It could be a local maximum, it could be a saddle point, right? Okay, now how do we prove this formally? We can use what we have seen so far, right? So we know that along every feasible direction, the directional derivative should be greater than or equal to 0, right? So if x star is an interior point, we know that every v is a feasible direction. Right, as is an interior point. This means that so v is a feasible direction, correct? Which means that the inner product between v and f of and gradient f of x star, this should be greater than or equal to 0, correct? But if v is a feasible direction, then minus v is also a feasible direction, right? Which must mean that minus v dot product with f of x star should also be greater than or equal to 0. But what is this equal to? This is just minus dot product between v and f of x star. So this implies that dot product between v and gradient f of x star should also be less than or equal to 0, right? If I just combine these two, I get that for every feasible direction, the dot product between v and f of x star should be equal to 0. Right? When can this happen? Only if the gradient is equal to 0. So for something to be an interior point, the grade, or for an interior point to be a local minimum, the gradient must be equal to 0. Okay, let's see a quick example. Right, suppose that my omega is the first quadrant. So this is set of all x in R2 such that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. And my function f of x is equal to, say, x1 square plus 0.5 x2 square plus 3x2 plus something 4.5. It's some polynomial in two variables. We can just have a quick look, see what this is. Plot it to 3. This is x1 square plus 0.5 x2 square plus 3 x2 plus 4.5. This is what the this is what it looks like. Right, some surface, and this is the region. Right, so we're only looking at x greater than x1 and x2 both being greater than or equal to 0, which is the region beyond this. Correct? Now, if you had to guess, what would be, which would be the local minima here? 0, 0. Visually, if you look at it, 0, 0 would be a local minimum, but every other direction, no other direction should ideally be a local minimum. Let's try to verify that. Okay, so So firstly, let's compute the gradient. What is gradient f of x equal to? Two x1 x2 plus 3, right? Okay, let's find inner product between gradient f of x and v. This is 2x1v plus x2 plus 3 times v. v1, v2. Okay, so let's take any okay, so firstly, if you take any interior point or any x1 x2 which is greater than or equal to 0, is the gradient ever equal to 0? No, right? For every x1 x2 greater than or equal to 0, this gradient is never equal to 0. So no interior point is a local minimum. Okay, that's good. Now we have to verify whether there are other points which are local minima or not. And that you can't simply verify just by looking at the gradient or whether the directional derivative is 0 or not. Right? So we have to verify that for every direction, the directional derivative is positive for it to be a local minimum. So let's pick some. Okay, so first let's eliminate the easy thing. Let's take x1 equal to x2 equal to 0. Right, so it's the point 0 comma 0. We guess that this should be a local minimum. What is the directional derivative equal to? Let me call this dv. dv is equal to v2. Okay, so how do you determine whether this particular point is a local minimum or not? At the point 0 comma 0, what are feasible directions? Yeah, correct. And v1, correct. So at 0 comma 0, so at this point, the feasible directions are whatever set of all v such that v1 greater than or equal to 0, v2 should also be greater than or equal to 0. Only then is it a feasible direction, right? And whatever norm v should be equal to 1. But v2 is greater than or equal to 0 implies that dv is greater than or equal to 0. Note that the directional derivative is not positive for all directions. It's positive only for feasible directions. Right? There is a direction which is not feasible where the directional derivative can be 0. Just take v2 to be equal to -1. Right? Okay, so therefore 0, 0 is a local minimum. Right? Let's pick some other point. Take. Okay, what are the boundary points? What do boundary points here look like? Correct. So it's either of the form x1 0 or 0 x2. Right. So let's take a boundary point of the form x1 0, where x1 is something that is maybe strictly positive. What are feasible directions? Yeah. Okay, correct. So V2 should be greater than or equal to 0. What about V1? It can be anything, right? So effectively, if you sort of draw a picture, right? This is my x1 axis, this is my x2 axis. The feasible region is, so this is my omega, correct? And I'm looking at some point which is x1 comma 0, which is perhaps a point that lies here, right? So in here, any feasible direction, so anything that points inwards is a feasible direction. And in particular, x1 could be negative or positive. So feasible direction is something that points to the left. That is something where x1 is less than 0, or sorry, v1 is less than 0, and to the right implies v2 is, oh, sorry, v1 is greater than 0, but v2 always has to point inward, so v2 should be greater than or equal to 0. Okay, so in this case, what is the directional derivative equal to? It's 2x1 v1, because v2 is because x, okay, sorry, 2x1 v1 plus 3v2. Right, so v2 has to be greater than or equal to 0, and v1 could be arbitrary. So is there a choice that makes dv less than 0? Yeah, basically, let's take v1 to be minus 1, v2 to be equal to 0. Which basically corresponds to this direction here. Right? And as we saw in the plot, right, you take any point here, if you move along this direction, the function value is just decreasing. Right? So that point cannot be a local minimum. Likewise, if I look at the x2 direction, then as I move towards 0, the function value is decreasing. So even those boundary points cannot be local minimum. right? Fine. So this gives us some necessary conditions, but again didn't give us any sufficient conditions. Now let's look at some more conditions. Suppose we have both the gradient as well as the Hessian. Then can we say something more? Okay. So even before that, now what happens if the gradient of f at a boundary point is equal to 0? Or let me put it in the following way. Suppose that along every feasible directions at some boundary point, the gradient is equal to 0. Sorry, the directional derivative along every feasible direction is equal to 0. Yeah, it is a minimum. Yeah, the minima may not be unique. That is fine. When we're not particularly worried whether the minimum is unique or not. Right? But for example, could it be a local maximum? Yeah. Potentially, it could be a local maximum also. So then, how do we decide? Or maybe to put it in a different way, suppose that x star is a local minimum. It tells us something about directional derivatives, but what does it tell us about second order directional derivatives? Or what can the Hessian tell us in terms of whether this point is a local minimum or not? So suppose that x star is a local minimum, and the gradient of f at x star is equal to 0. Okay, at this point, it so happened that the gradient is equal to 0. This potentially could be a local minimum, it could be a local maximum also. Or it could even be a saddle point. Right? That's perfectly possible. So, in particular, let's maybe to give you a concrete example. Right? Let's take x. Let's take omega to be equal to minus infinity to 0, set of all non-negative real numbers, and f of x equal to x cube, right? Now, what can you say about the point 0? Is this a local minimum? It's a local maximum, right? But then what does the first derivative test tell us? What is the derivative of f at x equal to 0? It's equal to 0, right? So it's not enough to tell us concretely whether this is a local maximum or a local minimum. So, so then it could be helpful to know something about the second derivative. So if x star is a local minimum and the gradient of f happens to be equal to 0, then for every feasible direction, direction v, we must have v transpose the Hessian of f at x star times v. This should be greater than or equal to 0. Which one? It can be equal to 0. Again, these are all necessary conditions. It's not sufficient. Just because these conditions, if this is equal to 0 and this is equal to 0, it could be a local minimum, it could be a local maximum, or neither. But if it is a local minimum and the gradient is equal to 0, then this quantity must be greater than or equal to 0. You cannot have this to be less than 0 for some feasible direction v. Okay. So these tests don't guarantee that yes, it's a local minimum or a local maximum. But if these tests are violated, then you can conclude that yes, this is not a local minimum. It's sort of a negative test. If this is less than 0, then yes, this is not a local minimum. But if it is greater than or equal to 0, could be a local minimum. Right? Again, proof is straightforward and follows exactly what we did earlier. Suppose that it's not true. That is, for some direction v, suppose that v transpose Hessian v is less than 0, maybe it's equal to some minus epsilon, then again you can use Taylor's theorem, right? You can write f of x to be equal to f of x star plus gradient f of x star transpose x minus x star plus x minus x star transpose the Hessian at x star times x minus x star plus some g of x minus x star, where this quantity decays much faster than norm of x minus x star the whole square. Right? So f of x plus delta times v is nothing but f of x star. Now we assume that the gradient is equal to 0, so the second term is 0, plus x minus x star is just delta v. So this would just give me delta square times v transpose Hessian times v plus g of delta. Again, if you for sufficiently small delta, this quantity is less than 0 for all small enough delta, which means that this cannot be a local minimum. Okay, but the second order test tells us something about so this happens if for x to be if x star is an interior point, then the second derivative test gives us not just a necessary condition but also a sufficient condition. So if x star is an interior point, and let's say at x star the gradient is 0 and the Hessian, so v transpose Hessian v should be greater than or equal to 0 for all v, because every direction is a feasible direction. That's the same as saying that the Hessian is PSD. If this happens, then x star is a local minimum. How do we prove this? Again, the high level idea is still the same. You just take the second order Taylor series approximation around x star. So you can write f of x plus delta times v to be equal to f of x star plus the gradient we know is, we are given that this is equal to 0, and this quantity, this is positive semi-definite, that's what we're told, plus delta square times v transpose Hessian v plus g of delta, where this g of delta decays much faster than delta square. Okay. But now let's go back to sort of the definition of a local minimum. Right? We want to make sure that for every feasible direction, this holds. Should be less than or equal to f. Right. In fact, you can prove something that's a little stronger. So if you look at the following quantity, V transpose AV, where A is some positive semi-definite matrix, in fact any symmetric matrix, you can derive both upper and lower bounds on B transpose AV in terms of the eigenvalues of A. The claim is that this is less than or equal to norm B square times the largest eigenvalue, and this is greater than or equal to norm V square times the minimum eigenvalue. Again, it's not very hard to do this. Just use the fact that the eigenvectors of V, or you can select the eigenvectors of A to be an orthonormal basis for Rn. Using that, try to prove this particular statement. Okay, so this means that this whole quantity del V transpose f of x star times V, if V is a unit vector, then this quantity is greater than or equal to lambda min. And A is a positive semi-definite matrix. Okay, I made a little bit of an error over here. I should say that if it is positive definite, then you're guaranteed that this is a local minimum. Just positive semi-definiteness need not guarantee that it's a local minimum. It could also be a local maximum. For example, if you take, let's say, f of x equal to x cube, right? What is the second derivative of x cube at x equal to 0? It's 0, right? But it's not a local minimum or a local maximum, right? So if del square f of x star is positive definite, then you're guaranteed that this is a local minimum, because then this quantity is greater than or equal to lambda min, and lambda min is something that is strictly positive. So this quantity is strictly greater than 0. This is, the right hand side is strictly greater than f of x star. Okay, so these two conditions are required for you to guarantee that some point is a local minimum. The gradient is equal to 0 and the Hessian is positive definite. Positive semi-definiteness is in general not sufficient. It need not be a local minimum. Okay, so all of this was for arbitrary functions, right? We didn't really impose any other conditions on f except the fact that f has maybe first order and second order derivatives. The beauty about convex functions is that many of these just are not only necessary, but they're also sufficient conditions if you know that f is convex. So if f is convex, and you happen to find some point such that the gradient of f is equal to 0, then f is then x star is the global minimum. Any guesses? Yep, you just use the first order condition. You know that for any x, f of x is greater than or equal to f of x star plus gradient f of x star times x minus x star. Right? We know that the gradient of f of x star is equal to 0, which means that this is equal to f of x is greater than or equal to f of x star for all x. Right? So it's a very powerful test. So just that additional information that f is convex just tells you that x star, if the gradient is 0, then x star should be a global minimum. Any questions? Okay, so this is a good point to stop. In the next few classes, in the next 1 or 2 classes, we'll start looking at algorithms for actually minimizing convex functions. Right? We'll start with designing algorithms that minimize convex functions on R, and then we'll use that to design algorithms to minimize convex functions over Rn. Right? So these will be similar to sort of, at least for Rn, we'll design algorithms that look similar to gradient descent that you've already implemented in assignment 1. But in assignment 1, you saw that there were some issues with gradient descent, right? If the function is not convex, of course, gradient descent could just take you somewhere off. But even if the function is convex and you don't choose your step sizes carefully enough, again, the function could just behave wildly. So that's always a problem. So then how should you choose your step sizes? Is there a systematic way of doing so? And is there a way of modifying gradient descent so that you're guaranteed to reach the local minimum eventually? That's what we'll see in the next few classes. Right?
Third term in the table.
The third term. So okay. So in this case, the second term is going to be what? It's a 2 by 2 matrix. Sorry, a d by d matrix. right? The second derivative, so to speak. What does the third derivative look like? It's going to be a third order tensor, right? So df square, the second order derivative, this is in Rn by n, assuming that, so if f is from Rn to R, then df square is in Rn by n. Df cube, the third order derivative, is something that belongs to Rn by n by n, right? It's nothing but the derivative of this, correct? This is okay? Fine. So I can represent this as df cube of ijk, right? So the third term in the Taylor series expansion would basically look something like this. So this would be summation overall ijk df cube of ijk of whatever. If I have x minus, let's say x minus x star, or x star minus x, this is evaluated at, say, x star, then this would be x star I minus xi times xi star xj star minus xj times xk star minus xk. Alright. Similarly, the fourth term would be, again, it would be a fourth order tensor. It would be ijkl, and this would be coordinate I, coordinate j, coordinate k, coordinate l, summed over all possible coordinates I, j, k, l. Yeah, so for functions on Rn, the Taylor series expansion can look very, very complicated.